In last lecture, we explored bridge circuits. They work by creating two voltage dividers using resistors and a null detector, like a voltmeter, help us find the balance point when the voltage across it is zero. Today, we will delve deeper into a specific type, the AC bridge. The AC bridge is a network of electrical components that allows us to measure unknown impedance. There's a fancy way of saying resistance and reactance, or combination of capacitance and inductance. It works by balancing them against known ones. In this circuit, the bridge allows an input using AC excitation, where it is usually a sine wave voltage signals. And the analysis of bridge behavior is the same as previously, but this time the impedance replaced the resistance. The AC bridge offset is represented as E times Z3 times Z2 minus Z1 times Z4 divided with the sum of Z1 and Z3 multiplied with the sum of Z2 and Z4. When a null condition is met, the impedance will satisfy this relationship where Z2 times Z3 is equal to Z1 times Z4. Now let's see how an AC bridge works in action. Here we have a Wheatstone bridge setup. As we can see, all the resistors have been replaced by impedance, where we have Z1 equal to 1 kilo ohm, Z2 equal to 2 kilo ohm, Z3 1 kilo ohm. We have a capacitor here connected to Z3, which is 1 microfarad, and the unknown Zx, which consists of Cx and Rx that we would like to calculate or find out when the bridge is null. Because the bridge is at null, so we have this condition where Z2 times Z3 is equal to Z1 times Zx, or R2 times R3 minus J over omega C is equal to R1 times Rx minus J over omega Cx. After we do some arrangement, so we will get in this form where R2, R3 minus J R2 over omega C is equal to R1 Rx minus J times R1 over omega Cx. If we look here, we have two parts where we have the real part and we have the imaginary part. So both parts must be independently equal. So we can create two equations where Rx equal to R2, R3 divided by R1 and Cx equal to C times R1 over R2. After we put in all the values for R2, R3 and R1, so Rx is equal to 2 kilo ohms and the Cx value is 0.5 microfarad. Act as a translator. They take changes in resistance, often from sensors measuring things like temperature or pressure, and convert them into variations of voltage. Voltage is a more universal understood language for control system. By converting resistance to voltage, bridge circuits provide a clear signal that this system can readily interpret and use for control purposes. The voltage signal from the bridge is always ready for immediate use. It might require further processing or conditioning to ensure it meets the specific requirements of the control system or an analog to digital converter or ADC. This conditioning might involve things like amplification, filtering, or scaling the voltage signals. The goal is to create a clean, accurate voltage representation of the original resistance variation. It is important to note that the variation of bridge offset is non-linear with respect to any of the resistor. Between the change in voltage delta V and the change in resistance, specifically resistor R4 in the bridge, isn't always perfectly linear. As you can see in this graph, when the resistance of R4 varies significantly, the resulting voltage change becomes progressively less predictable. This non-linearity can introduce error in our measurement. Imagine a sensor whose resistance changes perfectly in proportion to the quantity we're measuring, for this case like temperature. By using a bridge, we lose the perfect linearity, making it harder to accurately interpret the voltage signals. But fear not, there is a clever way around this. If we keep the range of resistance variation small, especially around the null point where the bridge is balanced, the relationship between the voltage and resistance becomes much more linear. Imagine the curvy graph is a bumpy road. By focusing on the small, relatively flat section of the road, we can navigate with more confidence. In this figure, it shows that when the R4 is between 90 to 110 ohm, then the variation of delta V with R4 on an expanded scale is relatively linear. And we can overcome the issue of small voltage variation by using amplifier. Bridge circuits are fantastic tools for converting resistance variations into voltage signals. However, understanding the potential for nonlinearity is crucial. By keeping the resistance changes small and centered, we can ensure that the voltage output accurately reflects the variations we're interested in measuring. It's filled with a mix of signals, each with its own frequency. But what if we only wanted to hear a specific part of this symphony? A filter is a circuit that passes a certain band of frequencies while attenuating the signals of other frequencies. Basically, there are two types of filter. The first one is a passive filter, which include the low pass, high pass, band pass, and band reject filter. And the second one is active filter, such as op-amp with gain and feedback. C filter was built by using resistor and capacitor. For a low pass filter, this is the circuit for a low pass filter where we have V in, firstly connected to a resistor, and we have a capacitor which is parallel to the input. And the graph here shows the response of the low pass filter. From this graph, we can clearly see that when our F, the ratio of F over Fc, which is the critical frequency, is less than 1 or low, then this filter will allow this frequency to pass through. While for the higher frequency, it will be blocked out. And this is the ratio between V out and V in for a low pass filter. For the high pass filter, the circuit is arranged differently compared to the low pass filter, where first we have a capacitor and the resistor, which is parallel to the input voltage. And the response of the high pass filter, as shown in the graph, but we can clearly see that on the higher frequency, the signal will be passed through, while on the low frequency, it will be blocked out. And the ratio between V out and V in is calculated as shown. For the band pass filter, it is actually a combination between a low pass filter and a high pass filter. And in this graph, we can see the response of the band pass filter, where we can see this type of filter will only allow a certain band of frequency to pass through while blocking the lower and higher frequency of the signals. We also have a selected type of filter where we have a reject filter, where in this combination, you can see this filter will block out a certain range of filter marked by lower FL and FH. So it will only block this range of frequency or allowing the lower and higher frequency of the signals. It's described in terms of output voltage to input voltage, or V out over V in at different frequency, and it is expressed as a measurement in decibel, where it is equal to 20 log of V out over V in. In a control system, the signal source for a data acquisition system is coming from a transducer, and the maximum bandwidth of most transducer is 10 Hz. Thus, filtering noises from this transducer signal can be done by using a low-pass filter. An example related to this RC filter. Let's say a measurement signal with amplitude of 540 millivolt has a frequency of less than 1 kHz. There is an unwanted noise at about 1 MHz. A filter is needed to eliminate the noise from the signal. Can you identify the filter type and why? From this information, we can say that in this example, we need a low-pass filter. Why a low-pass filter? Because the low-pass filter will block the high frequencies and passes only the low frequencies to the next system. Thus, the filter needs to pass 1 kHz of signals and block the 1 MHz signals. It means it will pass the low frequency and block the high frequency. That's why, in this case, a low pass filter is suitable for this situation. There are other examples where we can see the filters are needed. So this is a list of other examples. And we will look into this example during our tutorial session. Now let's move on to another instrument in analog signal conditioning. So now we'll discuss about operational amplifier or op-amp. An op-amp is a circuit consists of resistor, transistors, diode, and capacitors. This op-amp requires bipolar power supply, which is positive Vs and negative Vs with respect to the ground. And we concern only with its input and the output signal. This is the schematic symbol of a op-amp, where we can see it has two inputs and one output. And if you can see, V1 is connected to the positive sign and V2 is connected to the negative sign to represent the bipolar power supply. In op-amp, this is the internal circuitry of an op-amp, where we can clearly see that it consists of transistor, resistor, and a couple of diode, and also a couple of capacitor inside it. In terms of characteristic of op-amp, the voltage output or the output voltage V out is plotted versus a differential input voltage V2 minus V1. And we can see that when V2 is much larger than V1, the output is saturated at negative V set. While if V1 is much larger than V2, or on this left side, the output is saturated at the positive V set. In between, there is a narrow range of differential input voltage delta V, where the output change from positive V set to the negative V set. For most op-amp, this input voltage range is less than a millivolt, whereas the saturation voltage are typically on the order of 10 volt. For an op-amp, the input impedance are very high, typically exceeding 1 mega ohm, while the output impedance is very low, which is typically less than 100 ohm. So we can conclude that the characteristic of a practical op-amp are: first, it has a very high voltage gain. Second, it has a very high input impedance. Third, it has a very low output impedance. And lastly, it has a wide bandwidth. Where can we use this op-amp in instrumentation? So this is a list of application of op-amp in instrumentation, where the first one, we can use the voltage as a voltage follower. Second, we can use it as summing amplifier, or we can use it as a differential instrumentation amplifier. We can use it as differential amplifier, and last but not least, we can use it as instrumentation amplifier. For op-amp, there are two types of setup. Either it is inverting or non-inverting amplifier. Let's look deeper into how to use this op-amp inside each different cases. For the voltage follower, so the unity follower is a special case of the non-inverting amplifier, where all the output voltage is fed back to the inverting negative input, or to the inverting or the negative input by a straight connection. It will provide a gain unity of 1 with no polarity or phase reversal. From this equivalent circuit, it is clear that V out will be equal to V in. Now let's look at the inverting amplifier. This is the setup of an inverting amplifier, where we have R1 and R2 connected, where R1 is connected in between V in and the negative voltage input, and we have R2 connected to the feedback loop of output to the negative channel. And if we do the circuit analysis, we can come up with this relationship, where V out is equal to negative R2 over R1 times V1, and the inverting amplifier closed loop gain AV, which is equal to V out over V in, which is equal to negative R2 over R1. In this setup, the I1 plus I2 will be equal to 0. Amplifier, the setup is the other way around, where the V in will be connected to the positive input, and on the negative input channel, we will connect a resistor R1 and also a feedback from the output that passing through the resistor R2. And from this circuit analysis, we have a new relationship where V out is equal to 1 plus R2 over R1 times V1, and the non-inverting amplifier closed loop gains AV is given by 1 plus R2 over R1. And if we want to use the op-amp as a summing amplifier, so this is the circuit for a summing amplifier, where we have three resistors, R1, R2, and R3, and both our input voltage will be connected to the negative channel of the op-amp, while the positive channel will be grounded. And if we do circuit analysis, okay, we can see this relationship where V out is equal to negative R2 multiplied with V1 over R1 plus V2 over R3. Look at this example. Develop an op-amp circuit that can provide an output voltage related to the input voltage by this equation, where the V out is equal to 3.4 of V in plus 5. So what are the strategies that we will use to solve this equation? So there are many ways to do this. We can use a summing amplifier with V in on one input and 5 volt on the other, and we will choose a gain to be 3.4 and 1.0 respectively. The summing amplifier in the first stage is also an inverter, so a second amplifier with a gain of -1 is needed to make the sign correct. And we need to do selection of the value of resistor that based on the general notion of keeping the currents in milliampere. So the basic idea is we will have two. So it is actually a combination of a summing amplifier and an inverting amplifier. So on the first stage, we will need to identify what is the R1, R2, and R3. And on the second stage, we need to find out what is R1 and R2. So based on the relationship, so we know that V out for a summing amplifier, V out is equal to negative R2 times V1 over R1 plus V2 over R3. So what is our V1 and what is our V2? In this case, our V1 will be equal to plus 5 volts, and our V2 will be equal to V in. So we replace this inside this equation, so we'll get V out is equal to negative R2 times 5 over R1 plus V in over R3. Our V out should be 3.4 V in plus 5 volts. So if we compare between these two equations, so that we know that R2 over R1 is actually equal to 1. So R2 should be equal to R1, and R2 over R3 should be equal to 3.4. So R3 will be equal to R2 over 3.4. So if we choose R1 equal to R2, both equal to 34 kilo ohms. So our R3 will be equal to 34 kilo ohms divided by 3.4, which is equal to 10 kilo ohms. As for the non-inverting amplifier, because our gain is -1. So V out is equal to -R2 over R1 times V1. So the value of R2 and R1 should be the same. And in this case, we choose both R2 and R1 as 10 kilo ohms. So now we can complete this circuit. Here is the complete circuit where we combine the summing amplifier and the non and the inverting amplifier to solve the problems. We can also use op-amp as a differential instrument amplifier. There are many instances in measurement and control system in which the difference between two voltages need to be conditioned. A good example is the Wheatstone bridge, where the offset voltage, which is delta V, is the difference between VA and VB, where the quantity or the value of delta V is the quantity of interest. So for a differential instrument amplifier, V out will be gain multiplied with delta V, where A is the differential gain. So how the circuit will look like? So this is the setup of a basic differential amplifier configuration, where both sources will be individually connected to the negative and positive channel of the op-amp, where we have, for both input, we have R1, and on both channel will be connected to a R2 negative. On the negative channel, you take a feedback from the V out, and for the positive channel, the R2 will be connected to the ground. And the relationship between the V out and V1 and V2 will be like this, where V out is equal to R2 over R1 times the difference between V2 and V1. Usually, an exponential amplifier will include a voltage follower at the input side. So between V2 and V1, so we will put, or we use a voltage follower for input isolation. Let us look at an example related to this topic. Let's say we have a high impedance sensor output range of 20 millivolt to 250 millivolt, as the variable varies over its range. Develop signal conditioning so that this becomes 0 to 5 volt. Then develop the circuit. Approach problems in this sort is to build a linear equation where V out is equal to MV in plus V naught. We know that we want to convert the range from 20 to 250 millivolt to become 0 to 5 volt. From this information, we can produce two equations. So where 0 volt is actually equal to M times 0.02 plus V naught, and 5 is equal to M times 0.25 plus V naught. So we have two equations with two unknowns, and if you solve this, you will get M is equal to 21.7 and V naught will be equal to negative 0.434. So the complete equation will be V out equal to 21.7 V in minus 0.434. So from this equation, we can clearly see that we can use a summing amplifier, or we can use the previous solution in the previous example to solve this equation. Or we can rewrite this equation as follows, where V out is equal to 21.7 times V in minus 0.02. So in this second form, instead of using a summing amplifier, we can use a differential amplifier to solve this. And this is a differential amplifier circuit that we can use, where V2 will be connected to V in, and V1 will be connected to a input voltage with a value of 0.02 volt. For R1, we can choose a value, same value as for 10 kilo ohm. While for the R2, in order to make the gain as 21.7, so R2 and both R2 should be equal to 217 kilo ohm. Configuration of instrumentation amplifier is shown in this figure. This circuit allows for selection of gain with certain limit by adding adjustment of a single resistor RG. The relationship or the transfer function for this circuit is given as follows. Where in this circuit, the input impedance is very high and the output impedance is very low. Many IC manufacturers provide this circuit with fixed different gain and R1, but allow the user to insert external RG so that they can choose the desired gain to be used. In this example, this figure shows a bridge circuit for which R4 varies from 100 ohm to 102 ohms. Show how an instrumentation amplifier could be used to provide an output of 0 to 2.5 volt. Assume that R2 is equal to R3, which is equal to 1 kilo ohm, and that R1 is equal to 100 kilo ohm. So this is the bridge, the setup of the bridge. So how to solve this? So we will connect VA to the V1 input channel and VB to the V2 input channel of the instrumentation amplifier. So how to decide the value, the other value of R1, R2, and R3 for the circuit? So clearly that the bridge is a null when R4 equal to 100 ohm. So when R4 change to 102 ohm, the bridge will be not in the null condition and has an offset value, and we can find it by using this equation. And it seems that the delta V will be equal to negative 24.75 millivolt. The negative sign shows that the VB is greater than the VA. So to get an output of 2.5 volt at 102 ohms, it means that we need a differential gain of A equal to 101. So from the equation, so we have the relationship where 101 is equal to 1 plus 200,000 divided by RG times 1000 over 1000. Solving this, we can find that RG is equal to 2000 ohms. So note also that the input amplifier must be connected to the bridge with VA connected to the V1 and VB connected to V2 so that the polarity comes out correctly. Op-amp is as a voltage to current converter or V2I converter. Because signals in process control are most often transmitted as a current or pressure, for a current, usually it uses 4 to 20 milliampere. So it is often necessary to employ a linear voltage to current converter in the systems. So such a circuit must be capable of sinking a current into a number of different loads without changing the V2I transfer characteristic. So this is a setup for a V2I converter, where the input will be connected to the negative channel. And we have RL load on the output. And the relationship between I and V in as shown in this equation. Let's say we have a sensor outputs 0 to 1 volt. And we need to develop a voltage to current converter so that this becomes 0 to 10 milliampere. Specify the maximum load resistance if the op-amp saturated at plus minus 10 volt. To solve this, okay, so to satisfy 10 milliampere at 1 volt, we must have R3 equal to 100 ohm. And let us take R5 is equal to 0, which is allowed. So the equation also specify R3 will be equal to R4, which is equal to 100 ohms. This will complete the voltage to current converter, where the maximum load resistance can be found from the equation where RML is equal to 100 times 10 volt divided with 10 milliampere minus 100 divided with 200, where the maximum load resistance for this case will be 450 ohm. As for the I to V converter or current to voltage converter, it is usually used at the receiving end of the process control transmission system, where we need to convert the current back into the voltage. This can be easily done by using this circuit. So we have the op amp, the current will be connected to the negative channel, and the output will be connected to the control transmission system. And the relationship between the V out and input channel will be V out equal to I times R. Topic. If you need more information, feel free to flip these books, and thank you.